Alright, so welcome back to some videos. We are on Unit 3, page 1. So we're going to talk about rational functions and asymptotes to start with. You should know your unit test is going to be approximately 2 weeks. So this is going to be a quick unit. You notice the packet is not very thick, so we're going to get the information out and get reviews and move on. Alright, so we're going to talk about rational functions. We're going to talk about getting asymptotes, vertical, horizontal, and holes in rational functions. So to know what a rational function is, it's in the form of, so the function is some function over another function. So what this is saying, the rational function, so this is like the rational function, where the top and the bottom are polynomials. So this means something with like x plus 2 or x squared plus 3x minus 5. So there's multiple things on the top and bottom besides like a 1 and a 4 or a 2 and a 5. So there's going to be x's on top, x's on bottom, or possibly 1 just on the bottom, that sort of stuff. We did the introduction stuff today where we started looking at asymptotes. So vertical asymptote is always in the form x equals a, where a is a number. And the horizontal asymptote is like y equals b. So horizontal, side to side, vertical, up and down. So in this case, for the horizontal, b is also a number. Asymptotes are lines that the graph gets close to. They're usually dotted lines. The graph will get close to and typically do not go through it. And I do say typically because, as with a lot of math, you can do it most of the times, but there's always this one case. A graph can go through an asymptote if it's very, very close to 0. So there will be occasional ones where you might see them and there's going to be an asymptote, and near the origin, you might actually see the graph go through, and that's fine. That's the only place. So if you're out at positive 10, it can't go through that asymptote there. All right, so, excuse me. All right, to find the vertical asymptote, so I'm going to do like abbreviations with these. Vertical asymptotes, VA. Vertical asymptotes, we always take the denominator and set equal to 0. There are times we're going to have to solve for them. And times we don't. So on this first one, example A, the vertical asymptote is just x equals 0. So it's actually up and down. It's a line up and down through or alongside the y-axis. The one underneath it, let's just go to C here since it's there. A vertical asymptote happens when you set the denominator equal to 0. So don't even worry about the top. If there's an x on the top, that's fine. A vertical asymptote is the value x cannot be. So in something like this, x cubed minus x is equal to 0. Do some algebra work. Do a GCF of x cubed and x. Take it out. You got x squared minus 1. And then we can factor x squared minus 1 into x minus 1 and x plus 1. So this is very similar to the stuff we just did. On the bottom, the degree is 3. There should be 3 zeros here. Again, we're not finding imaginary ones for the denominator. So if they come out to be 3, that's great. If it comes out to be less than 3, like 2 or 1, you can't have a decimal of them. That's also fine. So we just need to find them. I did a GCF here, and then I continued factoring. All right, so for each piece, I have x equals 0, I have x minus 1 equals 0, and I have x plus 1 equal to 0. And then solve for each part. So you would have 3 vertical asymptotes, one at 0, one at positive 1, and one at negative 1. Okay. All right, so go ahead and work on letter B. If this B and D, if this is a good time to pause it, go ahead and pause it so you can try it and then match up. If you want to keep going, that's fine. So I take 4 minus x squared, set it equal to 0. You can definitely either factor, if you want to go the factor route, 2 minus x and 2 plus x. Or, because this is a number with the x, another way you can do it, as opposed to the one I just did GCF on, another way you can do it is just set equal to 0. Subtract 4 to the other side. Get rid of the negative, so divide by -1. Square root both sides. Okay, it is a quadratic, so it's possible it has 2 solutions. If you did the solutions over here, you would set 2 minus x equal to 0 and 2 plus x equal to 0. X equals -2 and x equals +2. Those are your vertical asymptote lines. Again, this last one, 5 minus 2x is equal to 0 for your vertical asymptote. And then x equals -5 over -2, which actually cancel out to be 5/2. All right, next step. So being able to go from a function that I give you and do the vertical asymptotes. Now what if I ask you to write a function that has a vertical asymptote of x equals 3? So this means with a vertical asymptote, this as a factor, so get the factor. Okay, so x is equal to 3. Move the 3 back over so it's with the x. So you have x minus 3 is equal to 0. So it's kind of reversing everything we just did. So I'm giving you the answer, and now you need to work backwards to what the problem was beforehand. So if this was your vertical asymptote, it meant this was on the bottom of a fraction. Now you can really write whatever you want. If you want to write x on the top, if you want to write 1000, if you want to put 3x plus 2x equal plus 5, that's fine. So it's really, the important part is they have x minus 3 on the bottom because that would create a vertical asymptote at 3. And then you can really have whatever you want on top. If you want to put the same 1 as I did, fine. If you want to put an x on top, an x squared, x to the 4th, all that's fine. All right, so when you're ready, flip it over to page 2. Excuse me. Now, we talked about vertical asymptotes, and now the next thing is going to be horizontal asymptotes. Now, this looks kind of really gross at the top. So, this whole blob means it's just a function. So, it's just a general form of what a function looks like without knowing the degree, without knowing the exponent, without knowing numbers in front. What you need to get out of this, though, is the degree in the top and the degree in the bottom. So the degree in the numerator and the degree in the denominator, and we need to compare them. So if n is less than m, so this means the top degree is less than the bottom degree. All right, so we're going to see some of these. The top degree of the top is less than the degree of the bottom. It's the horizontal asymptote is automatically y equals 0. So it's really the x-axis. If n equals m, the horizontal asymptote is the leading coefficient of the top divided by the leading coefficient of the bottom. So that means the number in front of the degree of the top and the number in the bottom in front of that degree, and just compare them in a fraction. If n is bigger than m, so is the top bigger than the bottom, there is no horizontal asymptote. Now we're going to get into slant asymptotes like you saw on the practice that we did, or the warm up to this bottom. and we'll talk about that later, but the degree on the top is bigger than the bottom. Right now, there's nothing to do, so there's no horizontal asymptote. All right, so here are some examples, some of each one of these. So the degree of the top on example 3 is 1. So I'm comparing 1 here with a degree on the bottom, which is a 2. I have a 1 versus a 2 for my degrees, and so I know my top is smaller than the bottom, so the 1 less than 2. So automatically the horizontal asymptote is y is equal to 0. Now the next one, I'm comparing the degree of the top and the degree of the bottom. So the degree of the top and the bottom are both the same. So this means you take the leading coefficient, so the number in front of both of those terms, and make the horizontal asymptote at that fraction. So I take them and say horizontal asymptote is going to be at y equals 2 over 3. Now, if it was something like 8 over 2, you would want to divide those out and make that a 4. But if it doesn't reduce, just leave it like that. Now find the horizontal asymptote for the next one and graph. Okay, we're going to worry about the graph right now. Degree of the top and the degree of the bottom. So 3 versus a 2. So this automatically means there's no horizontal asymptote. Technically, in the future, in a couple days, we're going to talk about if the top is 1 degree more, then it's going to be a slant asymptote. We'll talk about that. We're going to need to do some synthetic division for that, or long division, to be able to get the equation of the line. And we'll get there. Okay, a couple more things here. In the practice, the warm-up stuff, when a rational function has a factor in the numerator, cancel. So that's the thing. Cancel with a factor in the denominator. It creates a hole. Okay, so really you're going to see something in your graph that looks like an open circle. It means it doesn't have an exact value there because they would cancel out and make a problem or be a problem spot. Alright, so when you look at this function here, this is already factored for you. We may have to do factoring, we may not. X minus 2 and then x plus 4 and x plus 4. Cancel the factors that cause the rational function to the left, that cancel in the rational function. Alright, so we would cancel out those factors. So now the function is x minus 2 by itself. If there was other stuff, we would write the other stuff, but it's just x minus 2. Alright, so the whole is, so the denominator go to 0, or what you cancel out, set equal to 0. Okay, so what I canceled out was x plus 4. I set it equal to 0, and so I know my whole is going to have an x value of negative 4. The next part is if we plug the x value into the simplified equation, so the function is equal to x minus 2. If I go into this function, so I don't want to go back to my original. I want to go back to what I had when I canceled it out, so just the x minus 2. I'm going to plug in negative 4 and simplify and get negative 6. That is my y value, so negative 4 for the x, negative 6 for the y. So these two become an ordered pair, negative 4 and negative 6. So these are not lines now. This is going to be one point at negative 4 and negative 6 together. So I'm not going to worry about the final graph, but you should know at negative 4, negative 6, when we graph it, I would really draw a circle with an open spot to say that there's a hole there. Alright, so this is where we're going to stop. We're going to do some work with this and get some of the actual graphs and everything in there tomorrow. Let me know if you have questions. Thanks.